In section 8.1, we discussed a new type of coordinate called a polar coordinate. Up through now, everything that we have worked with has been something called rectangular coordinates. For example, if I said plot the point 2, 1, you would start at the origin and go to the right 2 and up 1 and put your point. Well, the polar coordinate system is going to use distances and directions to specify the location of a point in a plane. The ordered pairs for polar coordinates are going to be a little bit different. Instead of x and y, our polar coordinates are going to use r and theta, where r represents a radius from a central location, and theta is going to represent an angle. We've already talked about radii of circles and angle measurements in radians on the coordinate plane. This is going to work the same way. So we're going to start our polar coordinates by labeling the positive x-axis on a coordinate plane. Now, in trigonometry, we call that the initial or starting vector, or not vector, but ray. Now we're going to call this the polar axis. It starts in the exact same location. And then if you want to go to a positive angle, like 4 pi over 3, you would go counterclockwise. If you wanted to go to an angle like negative pi over 2, you would go clockwise. So to some, let's get rid of that arrow, to some point here, here's theta, and then r would be this length from, we'll call that either the origin, or it is also known as the pole. And that's where our ordered pairs are going to come in. Our graphs for polar coordinates are going to look a little bit different than what you're used to. Here's what a polar graph will look like. It'll look kind of like the coordinate plane, but it will have circles. And those circles have varying radii. So you'll see there's a circle through radius 1, a circle through radius 2, a circle through radius 3, and so on. This particular graph is in degree measures. However, we're going to do all of our work in radians. So let's do an example. I want to graph the polar coordinate 1, 3 pi over 4. The way this is going to work is you're going to start in your polar axis, in your initial position. And then 3 pi over 4 is going to be counterclockwise. That's where our positive angles are. Well, 3 pi over 4 is going to be over here. So we're going to go this way to get to 3 pi over 4. And then 1 says it is 1 unit in length away from the center, which is going to be here. It's going to hit the 1 radii circle. All right, let's try this again. 3 negative pi over 6. We always start with the angle, so we're going to start here on the polar axis. But this time, negative pi over 6 is the same as negative 60, so it's here. And then the 3 for r would represent 3 units away from the center, or a radius of 3. 3 pi. All right, again, we're going to start here on the polar axis. 3 pi says go in the positive angle direction. Well, if one full circle is 2 pi, then this must be 3 pi. So it's going to be over here, and then we're going to go 1, 2, 3 units away from the center. Here's the fun one. How do you have a radius of negative 4? Well, you don't. So this is how the problem's going to work. We're going to start on the polar axis, and we're going to go to pi over 4, which is over here. And then we're going to go 4 units out. The negative in front of the 4 is going to ask you to go the opposite direction. So here's the opposite direction, and then here is 4 units out. So this is where my final answer would be. So you start the problem like you normally do. You find the angle. You put a dot at the radius. But if the radius actually says negative, then you're going to go 180-degree turn from where you started. One of the things we talked about in trigonometry was the idea of the coterminal angle. So if I started with this angle pi over 6, I could add 180 degrees to it, or not 180 degrees, sorry, 360 degrees, or 2 pi radians, and I'd be in the exact same location that I started. But this location is now called 13 pi over 6. However, if I started at pi over 6 and I went clockwise a whole full circle, I would instead be subtracting 2 pi, in which case I'd be at negative 11 pi over 6. Well, pi over 6, 13 pi over 6, and negative 11 pi over 6 are all called coterminal angles. Well, it's going to work the same way with polar coordinates. If you add or subtract 2 pi, in other words, if you go a full circle around, your polar coordinate is going to be in the exact same location it was. Well, how about those negative radii? Let's say I had I'll go back to pi over 6. And I said that the radius was 3. We'll say 3's out here. Well, if it was instead negative 3, then your polar coordinate would be over here in the third quadrant instead. There's a 1 pi difference between those 2 points. And so you can also do the opposite of the angle, the opposite of the radius, and then take the angle and either add or subtract 1 pi. And you'd have the same location. So let's talk about the polar coordinate 2 pi over 3. Now, if you want to graph 2 pi over 3, pi over 3 would be about here, and this is where 2 pi over 3 would be. Well, we want to find other polar coordinate representations for this. Well, let's start with if r is positive, which it already is. If I were to take that point and go around in a full circle in the counterclockwise direction, I would end up at 2, 7 pi over 3. Or if instead I had decided to go in the negative direction, I would have ended up at 2, negative 5 pi over 3. If, however, I change r to be less than 0, that means I make r negative 2, then instead of adding and subtracting 2 pi, I'm going to add or subtract 1 pi, because remember that when you graph that radius, when it's negative, you go in the opposite direction. It's a 1 pi difference between the 2 points. So this one would be at negative 2, 4 pi over 3. Or you could have done negative 2 pi over 3 minus pi, in which case we'd be at negative 2 pi over 3. Sometimes we find it useful to change between polar and rectangular coordinates. So if we want to go from polar to rectangular coordinates, the x-coordinate of the rectangular ordered pair would be the same as r times the cosine of theta. And the y-coordinate would be r times the sine of theta. Which kind of makes sense if you think about when we talked about where a terminal ray would hit the unit circle at point P. We said that that ordered pair was the same as cosine theta, sine theta. If you want to go the other direction and go from rectangular to polar coordinates, then we're going to use r squared is equal to x squared plus y squared. That's gotten from the Pythagorean theorem of a right triangle on the coordinate plane. When we worked with right triangles on the coordinate plane, we said the side that lie on the x-axis, we called it x. The side parallel to the y-axis was y. And we called the hypotenuse r because it represented a radius of a circle. And then we also are going to want to use tangent theta is equal to y over r. This is going to be a helpful formula. We've used it before. So let's do an example where we're going to take a polar coordinate and change it to be in rectangular form. So what we're going to do is we're going to start with x is r times the cosine of theta. Well, in this case, the cosine of 2 pi over 3, first of all, 2 pi over 3 is in the second quadrant, so cosine is negative. And the cosine of anything pi over 3 is 1/2, so this is going to be 4 times negative 1/2, which is negative 2. Y is going to be 4 times the sine of 2 pi over 3. Sines in the second quadrant are positive, and the sine of anything with a reference angle of pi over 3 is square root of 3 over 2. So it's going to be 2 square root of 3. So the ordered pair is negative 2, comma, 2 square root of 3. Let's go the other direction now. Let's start with an ordered pair in rectangular coordinates and move to polar coordinates. The first thing that I want you to think about is what quadrant this ordered pair is in. This particular ordered pair is in quadrant 4. And that's important to know because it's going to help us out in a few minutes. So in order to go between rectangular and polar coordinates, we need to find two things. We need to find r, and we need to find theta. Well, we have this formula for finding r. Well, I know what x is. It's 2, and I'm going to square it. And y is negative 2, and I'm going to square it. So I'm going to end up with r equaling 2 square root of 2. But remember, when we take square roots, we can sometimes get positive answers and sometimes get negative. So I'm going to stick a little positive, negative sign in front of it. If you had told me the answer was square root of 8, that's fine. However, I challenge you to make sure your radicals are reduced because you'll need to do that on the ACT. Now I'm going to go and find the angle. And in order to do that, I'm going to use the tangent of theta as y over x. Well, the tangent of theta is negative 2 over 2, which is negative 1, and the tangent of negative 1, the calculator is going to give me negative pi over 4. That's because it's in the fourth quadrant. That's the same as 7 pi over 4, but we're not going to worry about that. Well, tangents are negative not only in the fourth quadrant, but also in the second quadrant. So 3 pi over 4 is in the second quadrant. Except that we want to focus on the fact that we want our ordered pairs to land in the fourth quadrant. So in order for that to happen, if we look at a coordinate plane here, we go, okay, if we start here on our polar axis and we go negative pi over 4, this point is going to be at square root, or 2 square root of 2, and negative pi over 4. Because you would go negative pi over 4, so you'd go in the clockwise direction, and then you would go a radius of 2 square root of 2. However, there's an angle we can get from coming over here to the opposite side, 180 degrees from it. That one we would get by doing 3 pi over 4, and then making r negative, because it would say go the opposite direction. So first you would go 3 pi over 4 over here, and then you would go off down in this direction because r would be negative. And it usually helps to draw a picture to figure out what ordered pairs are actually the solution to this problem. The next thing we're going to talk about is writing equations in polar coordinate form. So, most of our equations we use x and y. Well, we have ways of re-representing x's and y's now. Like we know x is r cosine theta in polar form, and we know y is r sine theta. If I square the left-hand side, I get r squared cosine squared theta. What I want to do is I want to solve this equation for r in order to put it in polar form. So I got to come up with a way of solving this for r. Well, this is what I'm going to do now. I'm going to divide both sides by r. So I get r on the left-hand side, but I'm also going to divide both sides by cosine squared. So on the right-hand side, I'm going to get 4 sine theta over cosine squared theta. I can probably leave the problem like this, but we don't usually leave trig functions in the denominator of a fraction. So I'm going to remind you, because cosine squared is the same as cosine times cosine, and sine over cosine is tangent, and 1 over cosine is secant, that r equals 4 tangent theta secant theta is a better way of representing that in polar coordinates. What if I want to go the other direction? What if I have an equation that's in polar form and I want to write it in rectangular form? Well, in order to do that, I want to get rid of the r and the theta. But how are we going to do that? Well, first of all, I want to remind you that r sine theta is the same thing as the y-coordinate, and r cosine theta is the same as x. So if I go and I divide both sides by secant, isn't 1 over the secant the same as cosine? And then isn't r cosine theta the same as x? I find out that r equals 5 secant theta is the same as the line x equals 5. And that's what its graph would look like. Let's try this again. R is equal to 2 sine theta. Well, this one, if I divide by sine, I'm going to get r cosecant theta. That's not going to get rid of my theta or my r. So I'm instead going to come up with another way of doing this. Sometimes you have to come up with a little tricky way of figuring out what the rectangular form of a polar equation is. So here's my little tricky way. I don't know what r is, but I know what r squared is. So if I multiply both sides by r, then r squared is x squared plus y squared, and r sine theta is y. Look at that. I have an equation in x's and y's. Now, what kind of an equation is that? Well, if I do a little bit of rearranging here, and I subtract and set it equals 0, and then I come over here and I go, that looks like a quadratic that I could complete the square on. And then this is what completes the square, and then I end up with this. Wasn't that the equation of a circle? It's very interesting to note that it's the equation of a circle, because the graphs of polar coordinates are going to be variations on the graph of a circle. We'll come back to that in the next section. Sometimes we have to do a little bit more work to get where we're going. If I look at r equals 2 plus 2 cosine theta, I can't convert anything right now. So I'm going to multiply everything by r, and I mean everything. So r squared becomes x squared plus y squared. I can't do anything with this r yet, but r cosine theta is x. Well, now if I do a little bit of maneuvering, I'm going to move my 2x over to the left. So because I still have an r left to get rid of, and multiplying both sides by r won't solve the problem, this time I could actually square both sides. And it's not a pretty looking equation, but it works. And then the right hand side is going to be 4x squared plus y squared. And then the left hand side just stays x squared minus 2x plus y squared squared. It's not pretty, it doesn't have a graph. However, that's how I get rid of all my r's and thetas and make it a rectangular equation. And that is an introduction into polar coordinates.